Okay, let's talk about valence electrons. Okay, valence electrons are going to be the outermost electrons that are most easily accessible. So most of the chemistry occurs with the valence electrons. And remember, at the end of the last section, I mentioned that term isoelectronic, okay, where we have the same electron configuration as something else. Once we become isoelectronic to a noble gas, we're not going to want to gain or lose electrons anymore because now we have that full octet and we're happy. The exception, of course, is going to be our transition elements because our transition elements have those d electrons, and so those d electrons, once we've messed with our s electrons, then we can get some interesting charges on our transition metals. But for the most part, we want to become isoelectronic to one of those noble gases. So our valence electrons occupy the outermost s and p orbitals. Okay? That's the key thing here, is the outermost s and p orbitals. So our d electrons are not considered valence electrons. All right? So when I look at something like silicon is in period 3. We're not messing with d electrons yet. And so silicon has its core electrons, the 1s2, 2s2, 2p6. Okay, so that's the electron configuration of neon. And then our valence electrons are everything we add after that. So silicon has 3s2, 3p2. Okay, so we have 4 valence electrons. Now what's interesting is if you look at silicon, it's in group 4a. Okay, well, what number is in front of the A? The number 4. So those group numbers that have A's after them, so 1A, 2A, 3A, 4A, etc., of the main group elements, so again, not the transition metals, but our main group elements with those A's after them, that tells us the number of valence electrons. So group 4A, silicon is part of that. We have 4 valence electrons. Okay. Here I have selenium. Okay. It is in period 4, so we do have d electrons. Okay, but this is after the transition metals. So selenium is in group 6A. All right. So in group 6A, I should expect to have 6 valence electrons, which I do. So I have 28 core electrons, and these guys right here are going to be the electron configuration of argon. And then after argon, we're going to add our 4s, our 3d, and our 4p. So again, the outermost s and p electrons are the valence electrons, and so I have 2 4s electrons and 4 4p electrons. 2 plus 4 is 6, so I do indeed have 6 valence electrons. Okay, and so if I look at some of these, my alkali metals, that is group 1A, so I have 1 valence electron, 2s1, 3s1, 4s1, 5s1, 6s1. Okay, so they all have the same number of valence electrons. My alkaline earth metals, group 2A. Okay, 2s2, 3s2, 4s2, 5s2, 6s2. Okay, they all have the same number of valence electrons. My halogens, that's group 7A. So I have 7 valence electrons. Okay, 2s2, 2p5, 3s2, 3p5, so on and so forth. My alkali metals, they all like to lose 1 electron, because again, metals like to make cations, and they want to look like the previous noble gas, and so I need to lose 1 valence electron for that. My alkaline earth metals like to lose 2 valence electrons to look like the previous noble gas. My halogens, nonmetals, they like to gain electrons, so my halogens will each like to gain 1 electron to look like the upcoming noble gas. So fluorine, for example, okay, 2s2, 2p5, if I gain 1 electron, I look like neon. Okay, chlorine, 3s2, 3p5, if I gain 1 electron, I look like argon. All right? And so that's how our valence electrons work. And then, of course, our noble gases over here, that's group 8A. They have 8 valence electrons. They're quote-unquote happy, and so they don't want to ionize. So that's why noble gases are very unreactive. And so these similarities in valence electron configurations is some of where we start to see some of our trends in the periodic table and why our groups have very similar reactivities to each other. Okay? And so our last section of this chapter will look at trends in the periodic table.